So we want to evaluate this integral. There's a typo, sorry about that. Though you could have done it the other way, but it would just have been sort of aggravating. So x squared plus y squared, it should be the square root of x squared plus z squared. So the region is bounded by the paraboloids, or by the paraboloid y is equal to x squared plus z squared, and the plane z is equal to 4. So now this is a paraboloid that is opening along the y-axis. Okay, so if this is the x-axis, this is the y-axis, this is the z-axis, the paraboloid is opening this way and is coming down to the plane y is equal to 4, or coming out to the plane y is equal to 4. And so this is a rough sketch of the figure that we're integrating over, or the region that we're integrating over. Well, this is a polar coordinates problem, because notice that if you take this region and you project it onto the xz plane, you get a circle. What is the radius of the circle? The radius of the circle is 2. The way that you can see that is that if y is equal to 4, that is on this plane right here, you have 4 is equal to x squared plus z squared. And so this is a circle of radius 2 in the xz plane. So since y is given in terms of x and z, that tells us that the y integral should be on the inside. So the y integral is going to go from a point on the paraboloid to the plane y is equal to 4. So in other words, y is going to go from x squared plus z squared to 4. And now we need to figure out what the x and z integral is. So the outer two integrals are going to be the x and z integral. Now we're integrating over a circle, like I said, in the xz plane of radius 2. So we should do polar coordinates there. So r is going to go from 0 to 2. Theta is going to go from 0 to 2 pi. The function that we're integrating is x squared plus z squared, or the square root of x squared plus z squared. So let me just be explicit. In the xz plane, we're doing polar coordinates. X is r cosine theta, z is r sine theta. So x squared plus z squared is r squared. You take the square root, that's r. Now you have the the dy, and then dr d theta, remember it's r dr d theta, but we don't want to write the r there, we want to write it here. So in other words, this is the integral. Theta equals 0 to 2 pi. R equals 0 to 2. Y is equal to x squared plus z squared, which is r squared, to 4. R squared dy dr d theta. So this is a good polar or cylindrical coordinates problem, whichever one you want to call it is fine. So again, the way, just looking geometrically at the picture, it makes the most sense to have the y variable be the inside integral. And looking at the description of the boundaries, that also makes sense because y is given in terms of x and z. And x and z are not given in terms of y.